Okay, good morning and good evening to everyone. Welcome to our seminar series between the VIT and Binghamton University. My name is Fudaning. On behalf of Dr. Muhammad Kasane, I would like to co-host this seminar today. And we're very delighted to have Professor Sugavaneswaran from VIT to give us a presentation regarding the additive manufacturing of multi-material structure, specifically talking about a futuristic modeling strategy. So Dr. Sugavaneswaran is a senior assistant professor in the School of Mechanical Engineering from VIT. He earned his doctorate in mechanical engineering from College of Engineering at Anna University, Chennai. His doctoral research involves integrating mechanics with material modeling of additive manufactured cellular and multi-material structure. Overall, he has published over 20 articles in the peer-reviewed international journals in this field. So let's welcome Dr. Sugavaneswaran to give this presentation. And thank you for joining us today. And I will turn it over to you, Dr. Sugavaneswaran. Thank you.
Yes, Professor. Thank you, Professor Fuda, for introduction. Good evening and good morning to all. In today's session, I'll be discussing on futuristic modeling strategy for additive manufactured multi-material structure. So at the outset, the outline of the presentation will be few basics of additive manufacturing and multi-material structure for those of you new to additive manufacturing, classification of additive manufactured multi-material structure, the significance of modeling in additive manufacturing, different modeling strategy used for various research activity. And before we go for a concluding remarks, I would like to share some of our research work which we are doing in our lab. Example like BioCAD modeling, bio-inspired modeling, uniform directional specific property modeling structure. So we had many sessions on additive manufacturing. The process is one among the different manufacturing process which converts a raw material into a desired shape. Most of the traditional manufacturing process are depending on tooling. If we take a formative, subractive or additive process, the tooling is a basic component. If we want to change a shape, if we want to change a material, the tooling plays a major role. The tooling could be a mold or die in formative process, tool insert in subractive process, jigs and fixtures in joining process. This restricts a lot in terms of development of new product, development of new designs. This paves a way for another category of manufacturing process, which is independent of tooling activity. One among that is additive manufacturing. As we can see from this animation, we could be able to demonstrate new models without the dependency of tooling activity. And apart from the independence in terms of tooling, we also have advantage, least wastage because of additive process, and the process is rapid response to the new design. If there is a change in design, the response to the new design is good in additive manufacturing compared to subractive manufacturing process. But still, there are a few restrictions. But considering this advantage, suitable application can be explored. Among the additive manufacturing process, we have different varieties. Few are powder based, few are filament based, some are resin based, some are sheet based. ASTM standard have classified this process into 7 major categories, and these categories are based on the principle in which the materials are joined and also the raw material form. So based on this category, we could able to see different process in market And this additive manufacturing process is mostly used for complex, customized, integrated gradient structure. Few of the example of additive manufactured component is displayed in this slide. It doesn't mean that these parts are not feasible in traditional manufacturing, but it is difficult to manufacture in traditional manufacturing. Some of the best example like customized component, synthetic feature component, complex component. This example is complex, customized, and material gradient, and integration of multiple functionality in a single component. So these are some of the well-known application in commercial aspects, the requirement of additive manufacturing process. If we look into the multi-material structure, the multi-material structure are majorly classified into two categories: graded type multi-material structure and discrete type multi-material structure. In graded type, the material from one behavior to another behavior will vary gradually. Whereas in discrete type, we could include the secondary material into the primary material in terms of fibers or particulate or flakes. So within the graded type, we can go for laminated, woven, isotropic, two-dimensional reinforcement, one-dimensional reinforcement. The fiber can be based on the L by D ratio. It can be a particulate, whisker, or laminate composites. So based on the functionality, we are using the multi-material structure in our application. And this multi-material structure, apart from composites, the other multi-material structure like graded structure are generally obtained through following process like mingling of two material, coating, sandwiching of one over another, uh, impregnation or intermixing the consolidated component, sometimes by using heat and pressure. And these are traditionally done through molding, welding, powder metallurgy, and coating and additive manufacturing process. But in this presentation, my focus would be more on how the graded or discrete type additive manufactured structure are made through additive manufacturing process. If we speak specifically to additive manufacturing, the multi-material structure are obtained through additive manufacturing in all the three categories: graded type, blended, and infiltrated materials. So in graded type, you can vary the material from one pixel to another pixel, from one layer to another layer. Blended type, material will deposit where the raw material itself pre-mixed. That is one primary material with a secondary material. In certain cases, it will be infiltrated. A scaffold or cellular structure will be fabricated using a single material, and this structure and density of the cell is based on the impregnation process what we are going to use and performance what we are expecting. So either through infiltrating medium, we could able to make additive manufactured multi-material structure, or through pre-mixed condition, we could able to make additive manufactured structure. And graded structure, that is pixel by pixel, we could able to control the material deposition. So this paves a new way of development called mesostructure. Generally, the performance of material is based on the processing condition and its microstructure. Whereas in additive manufacturing, the structure can be controlled. If it is in a multi-material condition, the position and orientation of different material can also be controlled in specific topology. And this topology can be designed in such a way that to obtain a specific property. So these are some example of mesostructure, which is very flexible to be manufactured through additive manufacturing process. And if we look into the existing literature, as I have mentioned earlier, In all additive manufacturing process, in all category like photopolymer, material extrusion, powder bed fusion, DED, sheet lamination, material jetting, binder jetting, through any one of the way like premix condition or graded condition or infiltrated condition, the feasibility of achieving multi material is there, and certain process have restriction in terms of material, ceramics, metal and polymers. So if we look into the photopolymer, it is mostly restricted to photocurable polymers. And among this 7 category, process has its own advantage and limitation. For example, VAT polymerization are good in accuracy, but it will take time consuming process, and you have less variety of material. Material extrusion fast, but dimensional accuracy is not that high as compared to photopolymer VAT. Powder bed fusion, you have wide variety of material, but there is a restriction in terms of thermal stress, residual stress, and material constraints. So from this, we could able to observe that by selecting a suitable modeling technique as per our requirement, we could able to achieve the desired material in desired pixel. So that is what the objective of this presentation is. Example is shown here. So it could be a random generation or based on the external loading, RVE can be repeated in 2-directional or 3-directional manner. So based on this input, uh, I would like to share some of the research works which we are doing in our lab with respect to modeling for additive manufacturing process, especially with respect to multi-material structure. So here we are working on fractal curves, fractal surface for electronics printing, and also few applications which required a high surface area in a given domain. Bio-inspired structure, uh, modeling of a material based on programming, CAD programming. So positioning and orientation of material, secondary material and a primary material based on CAD programming. Development of cellular structure, it could be analytical feature based cellular structure or synthetic structure like gyroid or nature inspired structure for bio application, as well as for compressive behavior, toughness behavior, mechanical characterization. We are developing few structures and testing it for its performance. So these are the some of the area which we are working on our lab. The next few slides, we would like to share some of our work with respect to this area. The first one is positioning and orientation of secondary material into the primary material. As I have mentioned initially, when we mix two different material, it can be of a different way. It can be a graded one or discrete one. Within discrete, we have option for one directional, two directional. It could be a particulate or viscous. So in this case, we have demonstrated the modeling capability of developing uniformly distributed secondary material into the primary material. So to demonstrate that, a known volume is taken, square shape known volume is taken with some thickness, and within this volume, the percentage of secondary material required is calculated, and based on the volume and percentage of secondary material, the number of reinforcement, that is number of secondary material should be generated within a given volume is calculated. So it required two input. The first input is volumetric percentage and domain of a volume. And the second one is volume of individual reinforcement. So here we have taken the individual reinforcement length and width based on the minimum capability of a machine, minimum width which it can print. So based on the secondary material dimension and the generated volume, with respect to volumetric percentage requirement, the number of reinforcement is calculated, and this reinforcement is generated in a given volume. That many number of reinforcement is generated in a given volume. So this has to be generated randomly. So we have generated a random number within a program itself. In this case, there was around 600, more than 600 reinforcement in a given volume. So 600, the position of 600 reinforcement, that is the position of the reinforcement in XY axis, is randomly generated using a Visual Basic Program script in a CAD software, and this reinforcement is randomly generated in a given domain until we achieve the desired volumetric percentage. And this can be repeated layer by layer by putting the program into the loop based on volumetric percentage requirement. So the material structure itself is designed, and this is a reinforcement which is freely deposited onto the Euclidean space. Now uh, the matrix material is drawn for the same volume, and it is subtracted for reinforcement and matrix. So the matrix is also drawn using a CAD software. Now we have a combination of matrix and reinforcement. The main objective is to generate a secondary material within a primary material in a uniform manner. Whatever we are going to develop in CAD, that will get replicated in printing, because as mentioned earlier, it is pixel to print process. So to check the randomness of the distributed material, in three directions the specimen is taken out, the two also in CAD model itself, and this three samples alone is individually fabricated using a Stratasys polyjet process, which supports multi-material printing. If we look into the distribution, so here I have displayed the distribution of a reinforcement angle, because the randomness of the reinforcement is calculated based on the angle. So for 360-degree, for each 30-degree, the number of reinforcement generated is plotted. So mean value is calculated based on number of reinforcement, and based on this mean, the normal curve is also drawn. So 90 percentage it is within 2 sigma level, and still even it depends upon the random method what we are using. So in this case we have used the method available in VB script. So based on the randomness method, the reinforcement is generated randomly, and the distribution falls within 3 sigma level. And these samples have been printed and tested, because the samples what we have taken out here is for a tensile testing. So the model to sample is printed, and the stress strain response of the printed sample is shown in this diagram. So if we look, there is a minor variation in ultimate strength, but if we look into the behavior of a material is almost constant, though we have generated the reinforcement randomly, but the uniformity is maintained only at the end, because it depends on the crack propagation region and how the reinforcement is positioned with respect to crack propagation region. So this is the unreinforced structure, and this is a reinforced structure, and the values obtained, Young's modulus and tensile strength value obtained for those three reinforcement structure is shown in this tabular column. So that is about the positioning and orientation of secondary material with primary material based on CAD programming. We have also tried to place secondary material within the primary material based on different loading condition. So this we took an reference from classical lamination theory, which is generally used for composite material. So if we look into the composite material, the positioning and layup sequence will help us to understand the behavior of a material, whether it is bending resistance or twisting resistance, or it had a superior strength at outermost layer. So this can be designed by using this CLT relation, classical lamination theory relation. So based on this relationship, A matrix represent axial loading, D matrix represent your moment, and B matrix represent the coupling between axial and moment. So certain terminology in this ABD matrix can be made into zero, and in certain sequence, certain layup sequence, we could also achieve symmetric condition in this laminate condition. That is above from the mid axis, above the mid axis and below the mid axis, we could able to achieve symmetric condition. So this based on this CLT relationship, the primary material is secondary material is designed into primary material, and this structure as well as the previous structure whatever I have discussed is fabricated through a polyjet three-dimensional printing process from Stratasys, which have a droplet of photopolymer deposition, and which will be cured immediately with the help of UV lamp layer by layer, and you have a inkjet ejection mechanism to eject multiple material within a layer. So that is one uniqueness of this process, which we can vary the material distribution within a layer also. So here the reinforcement and matrix I have taken based on the material feasible within the polyjet process. So Dyrus White, which is a commercial name, which has less strength compared to a Vellore material, which have high strength, 21 megapascal. So based on the CLT relationship, few stacking sequences are considered. The first one is unidirectional. All the three category are unidirectional, but unidirectional in longitudinal condition. So 3 represents 3 layer, and S represents symmetric of 3. So totally 6 layer. Above the axis it is 3, below the axis it is 3. So totally it is 6 layers. And 45, where all the secondary material is placed with the primary material in 45-degree inclination. 90 is the reinforcement is placed at 90-degree in all 6 layers. And based on this orientation, the relationship between the load, strain, and stiffness is shown here. So if we are placing only at the principal direction, 0 or 90, the coupling between the bending and axial load is completely eliminated. So based on the applied load, either the component may elongate or it may bend. But in all 3 cases, it is the coupling is 0 because we are using a symmetric condition. When we go for a symmetric condition, the coupling between the load will be 0. But the uniqueness of unidirectional composite is within the directional specific, that is within the tensile and shear load, the coupling is also eliminated, right? So this is bending and twisting. D66 is a twisting, and this is a bending stiffness. So the coupling between bending and twisting, the coupling between the tensile or compressive loading with respect to shear load is also eliminated in principal axis. So it says we can design a material in such a way that the secondary material can be taken, or the secondary material can be aligned to withstand the specific load. So based on our requirement, we could able to align the secondary material and the primary material based on the CLT guidelines. And apart from that, three more direction is also taken. That is bidirectional. That is, from one layer to another layer you will have a variable orientation. In the previous case, in all orientation we will have same direction. In all layer we will have same orientation of secondary material. Whereas the bidirectional, within a layer, within each with each layer we could able to change the direction. And again, the relationship is displayed in this equation, CLT equation. So the last one is a quasi-static, where we could able to achieve transversely isotropic condition. Now, the CLT guidelines will help us to design the secondary material from a primary material through a CAD model. So the unidirectional component stress strain behavior is shown here. So it is known that in tensile loading, if the reinforcement is, that is the high strength material is along the loading direction, will report the, we will get to know about the best strength. But in transverse direction, there is a delamination which occurs along the matrix. So if we look into the fractured specimen, we could able to observe that the load doesn't get transferred to the high strength material. The reason is, as we print a component layer by layer, within the layer we have a weak interface. So that is a most common thing in any additive manufactured component. Along the z-axis, the strength will be less, and this results in failure, catastrophic failure in transverse condition case. But at later part, I would like to show an interesting result, how we have eliminated or we have improved this behavior in unidirectional case. In multidirectional case, twisting, that is in plane and out of plane curvature, in plane deformation and out of plane deformation can be controlled by proper alignment of secondary material within the primary material. So like twisting, bending can be controlled, or combination of twisting and bending can also be controlled by choosing the proper alignment of the secondary within a primary material. So if we look into the fractured region of two bidirectional laminate, on the top it is cross ply, on the bottom it is quasi isotropic condition. So we could able to see 6 layers. So this top 3 layer and bottom 3 layer. So quasi isotropic condition, we could able to see the sawtooth profile of a fractured region, and this sawtooth profile is preliminarily due to the positioning of secondary material into the primary material. So the material is same for both case, cross section is also same. By selecting the suitable orientation, depends upon the loading condition, the behavior of the property, the behavior of additive manufactured multi-material structure can be varied, and also it can be taken in a reverse. According to our application, we can design the secondary material into the primary material. So these are all different output, tensile loading, shear loading, and bending loading. In all the cases, for a different condition it is displayed. One point I would like to emphasize here is, within each category, the loading condition, material and cross section is same, but we could able to achieve different response, different ultimate that is fracture strength for the same material. Now, what will be the benefit of such structure? Why we have to go for such different orientation? What could be the benefit? One example is the resin based process, even laser based process. We have a problem like residual stress. As we print a component layer by layer, the bottommost layer is getting more exposure compared to the top layer. Within the laser penetration also, we are not observing uniform profile. For example, in this case, the exposure of a UV light for a spot. So this is the spot size, that is Y, and with respect to depth, if you look with respect to depth, it gradually decreasing, but within the cross section at the center, it is very high. It is because of a Gaussian profile, which we observe even in UV light as well as in laser. So due to this variability and due to exposure of a laser to a subsequent material, maybe we can have a support to read to overcome the issue. But once we remove the support, especially in plastic material, that too in thin feature, while we remove the support, automatically it tend to curl, automatically it tend to bend. So researchers have worked on this heterogeneous behavior, and was reported that from layer to layer, the elastic modulus will get varied. And because of this change in elastic modulus, the material will get curled, especially it is more predominant in thin section. So what we have done is, according to the response what we get from a different orientation, we have designed a different L by D ratio with the different thickness, and the material, the same material is same thin strip is manufactured through single material condition as well as in multiple material condition. After removal of part from the component, the curl distortion in thin feature is measured. So this is a printed component of thin feature based on quasi-isotropic condition. So the enlarged image, we could able to see the multi-material condition. The dimensional combination we have taken shown here, a different width, different length, and different thickness combination for the purpose of experimentation. We could able to observe in-plane distortion as well as the out-of-plane distortion. Uh, As we have a specific property, as we are designing the material with a specific orientation, the comparison between the multi-material structure, though it is not an optimized one, we have taken directly the quasi-isotropic. It is not varied because at the bottom we have the Young's modulus is different from the top. So if we look into the curling behavior of thin feature, it is not, though it is not an optimized condition, but with the help of a quasi-isotropic, which have high resistance to bending at top and bottommost layer. So that is what we did observe even in finite element analysis. As we look into the ply-wise stress behavior of a material with respect to thickness, the quasi-isotropic condition have high strength, high resistance to the bending load. This is for a bending load. So in quasi-isotropic condition, the resistance is more at the outermost layer. So this three graphs shows the stress behavior across the thickness for a bending load condition. So the first one is for angle ply, the second one is for cross ply, and the third one we are having it for quasi-isotropic ply. As I have mentioned, the blue color line is for shear load. So in cross ply laminate, we do not have a coupling, so shear load is completely zero. So the results, whatever is displayed here, it is for multi-material structure and single material structure in out of plane condition as well as in plane condition. So now we are further working on calculating, that is through analytical method, calculating the individual elastic modulus of a layer, and accordingly varying the composition of primary material in secondary material across the thickness to control the distortion, that is anti-curling behavior has to be implemented, so that even after the removal of component it maintain the proper uh, st- without any deformation, it maintain the proper position. So this type of structure will play a major role, especially in compliant mechanism. Nowadays we are seeing a lot of application of additive manufacturing and compliant mechanism, topology optimization, thin structure, cellular structure fabrication. So we believe that optimizing the behavior, material distribution from bottom to top based on the variable elastic modulus, we could able to restrict the distortion in thin feature. So this is one example of a thin feature turbine blade component where it get removed from support, automatically it tend to curl because of a heterogeneous behavior. The other part of the presentation is, as I have mentioned earlier, in transverse loading we could able to see the load doesn't get transferred from matrix that is the softer material to a harder material, right? So as we are designing from CAD, we took an advantage of mechanical bonding, and the interface between the primary structure with respect to secondary structure is redesigned. Instead of planar interface, it is redesigned with a corrugated interface as we observe from nature. So the planar interface is redesigned into a corrugated interface, and this is subjected to bending. Whatever the image is displayed here, it is a failure of a component in uh, tensile loading. So as the corrugated structure are advisable for bending loading, the interface is the planar interface is redesigned with a corrugated interface, and it was printed using the same polyjet three-dimensional printing machine. The stress strain behavior of three combination, that is without the secondary material, only with the planar material, the maximum strength is around nearby 10 megapascal, whereas if we go for mixing primary material with secondary material, there are 6 layers. As it is subjected to bending load, we could able to observe the peaks, that is layer by layer fractured of all 6 layers, and this strength is less than that of the strength what we observe for pure material, virgin material. Whereas in corrugated structure we could able to achieve the drastic increases from 10 megapascal to 25 megapascal, and this problem, that layer by layer fracture problem, is also addressed by means of this corrugated structure, though it is not fixed at both end. We could report the result until this part. So the interface problem based on the CAD design, the multi-material structure interface can also be designed for additive manufacturing, which is exclusively for multi-material fabricated through additive manufacturing structure. And one more possible application of the stacking sequence could be soft robotics. Here you can see the application of laminate orientation. For example, in this case, the part is made through a smart material, and apart from the material behavior, the structure is also playing a major role. So as reported, the component is made of square cellular cavity, that is layup is like crisscross or cross ply. Here it is inclined ply, diagonal cavity. Just by changing the layup direction, we could able to control the distortion behavior of a material. And this distortion could be used according to our application. So that is another significant application of the positioning and orientation of material in it could be a cellular material or embedded material secondary into a primary category. And one more case study which we have completed working on in our lab is prosthetics fabrication. In this case, it is specific to ocular prosthetics. So this ocular prosthetics is also called as glass eye. This glass eyes are used for patient who have a glaucoma diseases or who got an injury. It is replaced by this cosmetic eye, though it doesn't have any functionality for cosmetic purpose, and also it serves certain functionality uh, like dust prevention and accumulation of tears and maintaining the proper distance between your eyelid after the surgery. So this could be a custom shell or a customized shell. Custom shell are available in market. It may not fit properly, as you can see from first figure. Whereas the customized shell, you cannot identify which is original and which is a customized one. And this customized surface will fit exactly to the profile of your eyeball. So there is a purpose of customization, but both are cosmetic. One is custom shell, another one is customized. One is a normal shell, and the other one is a customized shell. So to make this customized shell, the patients are subjected to multiple visit, and they will pour acrylic into the cavity. So they will put a wax into the cavity, and the wax impression will be taken out. And based on the impression, the mold will be prepared, and within the mold, the acrylic material will be solidified to achieve the final component. So you can see the difference. The purpose is to have a better cosmetic effect and also to mimic the surface, whatever the surface we are generating, it should mimic the surface on a ball. So this case, we have taken it for an additive manufacturing route. By using a CT scan, the cavity profile is measured, and based on the cavity profile, the three-dimensional CAD model is generated. And this is also fabricated through polyjet three-dimensional printing process, and the final implanted prosthetics you can see from this figure. So that is like image processing. There is a BioCAD modeling where we take an image and converting the image into a CAD model for application. So the functionality of this customized shell uh, was evaluated by using IPD measurement, that is interpupil distance between the center position to your pupil. So generally, the normal shell may not have a proper IPD distance. It may vary as you move your eye left and right. So the normal eye will move properly, whereas the custom shell glass eye may not move. If we want to have a better motility, few patients are going for peg implant. That is, they'll have a peg which get attached into the ball. So it is done through a surgery. Whereas through additive manufacturing process, we could able to replicate that structure. The IPD measurement for a few trials is displayed here. And the ocularist is also satisfied. And the most important advantage is it is patient specific. And if they lost the data, the patient need not to visit the clinic again. It is stored as a CAD model. Rework is also reduced as you go from wax to mold to acrylic. The precision is not high, so we could not able to observe such good IPD movement. though it is customized, whereas in additive, we could able to achieve the satisfied result. Better motility without the implant, without the peg implant, and dependent on skilled labor. So if we take in our country, we have a shortage for prosthetics, exclusively for ocular prosthetics. And at the bottom, I have displayed the market requirement from 2019 to 2027 for different continent. So these are all few benefits apart from the customization and technology they could able to achieve for this particular process. So overall, in traditional manufacturing process, the performance and behavior of a material is completely depending on the processing condition, whereas in additive manufacturing, the performance and behavior is controlled based on 3M: machine capacity, material capability, and modeling capability. The work, whatever I have shared from our lab, is mostly relevant to modeling. With the modeling technique, how we could able to achieve desired property, and this some unique output can be explored for new applications or for some of the existing application. I would like to thank from Bingtom as well as from VIT for giving this opportunity. And apart from that, in our lab, we are also working on continuous fiber printing of composite material. So through this forum, I would like to seek your expertise and collaborative research work for continuous fiber composite printing, especially for planar, non-planar direction and toolpath strategy. Thank you, Professor. Thank you.
Okay, thank you very much, Dr. Sugavaneswaran, for your great presentation onto this wonderful work in the area of multi-material additive manufacturing, and specifically, you have proposed the modeling process to design the structure. So this is a really great job. Now we are going to open it up for questions. If you have any question, please feel free to either unmute yourself or tap the question into the chat window.
Professor name?
Yes, sir.
Yes,
this is Prabhu, graduate student here from Binghamton. I have a question for Professor Sugavaneswaran. Very interesting applications and strategy you have, Professor. Great work. I like your presentation. I have a question on slide 15 of your presentation, where I think you had shown some structures. I think specifically they looked like fibers oriented in a specific direction. I wanted to know what the size of those fibers are, and actually, I'll wait for my question until if you want to go to slide 15. I wanted to know whether these kind of fibers can be grown on electronic thin films where we require nanowires. Is that something that is possible through additive manufacturing? What is your thought on that?
Yes, Prabhu. So the fibers diameter, whatever I have displayed, is around 0.5 mm. It is based on minimum resolution which we could able to report from the machine. So less than 0.5, we are unable to achieve the proper resolution. With respect to your question, micro level, maybe with this machine, it may not be feasible, but few researchers are working exclusively on micro additive manufacturing. So maybe that we could able to look into the minimum resolution what we can go for.
Okay. Thank you.
Thank you.
Any other questions?
Sir, actually, You mentioned you are able to print smart materials also using these methods, right?
Yes, sir. Yes, sir.
So in that regard, for example, nitinol, right? So this
Okay.
transformation is dependent on temperature, and how would you be able to control temperature precisely if you make a smart actuator out of this?
Okay, so in this presentation, the material what I have shown to you is photopolymer resin, not with respect to metal, but researchers are working on nitinol also. Maybe I didn't work on metal smart materials as of now, but I could able to see research work, but not in thin structure, maybe in bulk structure. A few publications are available, but the material whatever reported in the presentation is hydrogel and uh, photopolymer resins.
So can this be extended to nitinol? The next question.
Yes, nitinol. I went through few article in nitinol also.
Okay, great. Thank you, sir.
Dr. Sugavaneswaran, I have a quick question.
Yes.
So we know that the bonding strength is kind of a technical challenge, especially at the interface of the dissimilar materials. Do you have any chance to improve the bonding joints and performance, like using your material design or using the CAM programming to further improve that?
Yes, Professor. As it is mentioned, one mostly through other than the physical and chemical method, in my work mostly through mechanical linkage, I'm trying to improve the interface between the primary and secondary material. So one example I have shown here, that is using a sine wave between the laminate. And apart from that, we did a few work on dovetail linkage between the primary and secondary material. But again, we have a limitation in terms of resolution. So mission resolution beyond some microns we are unable to achieve. So that is the limitation I'm facing. But apart from the corrugated structure, textured as well as the dovetail linkages we have explored.
Right. And I believe this is a type of composite material, right? So you consider that as a multi-material, as you have the one of the resin is matrix and the other resin is reinforcement.
Yes.
Right. So apart from the material jetting process, have you ever utilized any other type of like laser-based AM process to print multi-materials?
No, laser-based process we haven't explored for multi-material condition.
Okay.
But cellular structure like gyroid, negative Poisson ratio structure, we could able to do. But still, the limitation is in terms of support structure. Beyond certain overhanging length, we are unable to print even a cellular structure also. But few gyroid shapes and gyroid shape we could able to eliminate for some radius. But in axotic structure, again, there is a limitation in terms of support removal.
Right. I see. Okay. Thank you.
And maybe to add to your question, we started work on laser scanning strategy based on classical lamination theory. So scanning strategy, which can be varied from one layer to another layer, and look into the performance in terms of distortion.
Okay, I see. So actually we utilize laser-based additive manufacturing like a DD process to print multi-materials. But as I mentioned earlier, that the bonding joint is a really a big challenge. Even though we have utilized functionally grading materials to generate transition layer, it is still a problem that we have to tackle. Okay, any other questions for Dr. Sugavaneswaran? Okay, if no further question, let's thank Dr. Sugavaneswaran one more time for a wonderful presentation today. Thank you very much for joining us.
Thank you, Professor. Thank you all.
Okay, and then next, I'm going to introduce the speaker for next week presentation. The speaker will be Muhammad Hindi, who is a graduate research assistant in CAM, working with Professor Mark Pollux. His presentation will be related to aerosol jet printing of the hybrid electronic components. And he will talk about the processing and performance assessment during this advanced additive manufacturing technology. And I believe Dr. Kasani will share this poster around earlier next week. So please send this to your colleagues and students. And we look forward to seeing all of you guys in the next week. Okay, this will be the end of today's seminar, and thank you very much for joining us again. We really appreciate your support in this joint webinar series between Binghamton University and VIT. Thank you very much.
Thank you, Dr. Fuda. Thank you very much.
Thank you. Bye-bye.
Thank you. Thank you.
Bye.
Professor. Have a nice day.